3, 2, 1.
Hello, I'm James O'Loughlin, and in this podcast we're exploring some new technology developed by Calix, how it was developed and what it can be used for. In EP 1 we discovered how the technology went from being just an idea in someone's head to a real live company with clients around the world. In this episode, a closer look at how this technology, a direct separation reactor, actually works. Phil Hodgson is the Managing Director and CEO of Calix. He joined Calix as CEO, came in at the top in 2013. He'd previously worked with Shell, then ran his own consultancy, providing project development and advice in areas such as biofuel, clean coal, geothermal energy, logistics, etc. G'day, Phil.
Hello, how you going?
How and why did you join Calix?
How? Yes, it's I left Shell and sort of around 2007. And I really wanted to do my own thing. And I started out a little consultancy business, and the skills and competencies I sort of learned at Shell in technology, but also in commercial and business. I started to work as a consultant and increasingly gravitated to new startup technology companies. And so one of the gigs I got in 2012 was doing some strategy work for a little company called Calix.
Oh, I see.
And I sort of fell in love with the technology and joined the company in 2013.
So it was the technology that excited you. Why?
I could see, I guess, my background's process engineering, and I could see that this was a company with quite a unique technology, processing technology. It was unique because it was so simple in concept, yet it could be applied to quite a few different things. And I was excited to sort of explore and see how it could be developed into a whole lot of different areas. And so that was what piqued my attention very early on.
And this is around the time they were still focusing, am I right, on materials for the building industry, which ultimately turned out to be not where the main competitive advantage is. Did you, when you joined, were you still thinking mainly building industry, or were you looking elsewhere?
Look, I think the building industry was a big focus for the company when I joined, but I was very intrigued on some products we were starting to make that was looking at water treatment. Even so, my very early research work when I was at university was in wastewater and water treatment, and so that sort of started to resonate as well. But I was also very interested in the particles that this technology was making, because these particles were a little different from other particles that I'd seen of the same material. And I was wondering what those particles could ultimately be used for. And, you know, as we go through the tech, I'm sure we'll explore how and what those particles are and how they're different.
We will. But to give people an example, tell me if I'm wrong, the particles are different because the process you're going to explain makes them more reactive than
Correct.
they would otherwise be.
Yep.
And if you think about wastewater, putting stuff in it to clean it, the more reactive that stuff is, the better. So if you've got a material that's more reactive than other materials, it can be far more effective in cleaning up wastewater. How am I doing?
That's pretty good, James, because you can imagine a sponge, you know, and the ability of a sponge to soak up water. Our little particles are like little tiny sponges, and so their ability to soak up things like phosphates and nitrates are all very important with respect to sort of wastewater treatment. So, yeah, it was those aspects that really interested me early on in the technology.
Okay, so now that the listener has got a picture in their head of little sponges soaking up yucky things in water, let's try and talk them through how this is actually created, and me actually. So Calix uses direct separation reactor technology to create those highly reactive materials. What is it?
Okay, so imagine a very tall and fairly wide steel tube,
Yes.
maybe nearly 2 metres in diameter and nearly 22 metres high. We've got one of those in Victoria in Bacchus Marsh. We heat that steel tube to 1,000 degrees centigrade, so it's glowing red hot. And anything we want to heat up any sort of mineral that we want to heat up, we grind to a small particle size, much like flour.
So why are you heating it up in the first place?
Because inside each one of those little particles are trapped gases. And when you heat it up, those trapped gases escape from the particle and they form a little pore as they make their way to the surface of the particle. Yeah. And so what we try and do in our big tube is get the temperature profile on the tube just right and get the time that the particle takes to fall down through the tube just right, so that we're maximising all of the number of those pores that get produced in the particle. And so that's ultimately at the end how you get a sponge-like sort of effect at the end. So under a microscope, you look at these tiny particles, you can see it looks like sort of a honeycomb type structure.
And you're doing that, am I right in thinking there is a relationship between the surface area of a particle, and if you can imagine a honeycomb-like structure has a very large surface area, the greater the surface area, the more reactive it is.
Absolutely correct. It's simple sort of chemistry, but the more surface you have, the faster reacting, and it's that sort of fast reaction that gives us competitive advantage in a lot of different areas that we're now looking at for these particles. Wastewater treatment's the first area, but there are other areas that we'll talk about as well.
So, what are you doing differently? Like calciners, the big tube that does this, they've been around for a while. What are you doing differently from a normal calciner?
Yeah, so the big tube is in fact the I guess the revolution here. A kiln or furnace has been around essentially in the same format for 5,000 years. Wow. And so typically there, what you're doing is mixing all of the fuel and the stuff that you want to heat up all together in the one spot and lighting a match. What we're doing with our tube is separating how you heat it from what you're heating. So we're heating the tube from the outside and keeping it separate from the stuff on the inside. And doing that, we don't get furnace gases that contaminate our particles. We can heat with any sort of medium we like. It can be gas or coal or biofuel or renewable electricity. So the technology is very flexible in the way that you carry out your heating.
So you're keeping the minerals separate from the combustion products?
Absolutely correct. That's right.
And that allows the carbon dioxide to be separated from it, which is unusual in a calcinator,
yes.
A calciner, is that right?
Yeah, so if you start with, say, limestone, and you're heating up limestone to make lime or cement, ultimately, half the weight of a lump of limestone is CO2 trapped in that rock. And so when you heat it our way, that CO2 is not getting mixed with all the furnace gases and then very difficult to separate at the end of the process. So it's coming out inside our tube. It makes its way to the top of the tube as a pure stream, already separated. And so that's why it's of interest to the cement and lime industries, who are sort of responsible for about 8% of global CO2 emissions.
So you then capture it?
Yeah.
You don't just pump it into the atmosphere, you can capture it and sequester it.
Capture it directly, exactly right. That's the advantage of the technology for that particular application with limestone.
Okay. So the reactor's a tall cylinder. How hot does it get?
We heat the steel up to about 1,000 degrees centigrade, so it's absolutely glowing red hot.
Crikey. And the mineral, you grind that up into a powder, you drop it in at the top, and it kind of floats down. It's in there for a little while, isn't it?
Yeah, it's sort of in there for about 20 to 30 seconds. And so that's just right to cook it just right, if you like, to maximise that porosity but have the full reaction go. Most kilns that can be in there for several minutes to several hours, and that we can do it in just a few seconds, and that makes sure we get the most reactive product we can get.
And you have a radiative heat transfer. Now, what is that and why is it important?
The radiative heat transfer is that glowing red hot tube. So a bit like the sun, the heat of the sun is radiative heat. It's because it's glowing so hot. That's like the walls of our tube. They're glowing red hot, and it's that radiative heat coming from the walls of the tube into the particles that gives the heat that we need to carry out the reaction. And
the reaction is endothermic.
Yeah.
And explain that.
Yeah. So endothermic is where...
I feel like I'm back at school.
Yeah, I know. So endothermic's the opposite of exothermic. An exothermic reaction produces heat. An endothermic reaction requires heat. Okay, so the reaction to heat up those particles and liberate those gases out of the particle is endothermic because we're adding heat to make that happen.
Okay, so you get a pure CO2 stream, you get the honeycomb structure that has a large surface area and therefore the material has greater reactivity.
Yep.
And you can also process quite fine materials that are perhaps too small for traditional calciners, is that right?
That's correct. So typically in a kiln you need pebbles or rocks of a certain size. Otherwise, remember all those furnace gases I told you about? Yeah. They'd be blowing all the material back out the top. So because we can separate the furnace gases from the material, we can calcine or heat up very small particles.
And just to blow people's mind about the surface area, on a little, I don't know, say a gram of these powder materials, what would be the surface area and how would it compare to materials from a traditional calciner?
So we're looking at up to 300 to 350 metres squared per gram of material.
No.
So 350 metres squared per gram. You can imagine like a decent sized sort of football field in just a gram of material.
Goodness.
That's 5 to 10 times the surface area that could be achievable with any other technology. So that's what makes our technology special.
Wow. It's pretty mind-blowing, isn't it?
Yeah, it's a lot of surface.
Yeah. So you've got these you've got these high reactivity, you've separated the carbon dioxide so that can be treated appropriately. To get this all working properly, and it is, it's doing it in various locations at the moment, what sort of challenges? I mean, the heat, the powder, must be a finicky business.
Well, it's interesting because when I first describe it to people and the first time they hear it, they say, well, you're just heating up a tube and dropping stuff down it. What could be so hard about that? Well, it's actually quite tricky. You overheat one area of the tube, it can distort, and you're at such high temperatures that the slightest distortion can be very bad for your process. If you don't get the pressure quite right, you can imagine this very hot tube gets quite flexible and pliable. You don't want to suck it in on itself or blow it up like a balloon either. And so there's all sorts of process control conditions that you need to operate really carefully so that you don't damage your tube. And so it's the control of that that's really important. And then you can imagine these particles floating down the tube. Just say you want to go a bit quicker or want them in the heat for less time, well, you can start to transport them down more quickly with a carrier gas, or you can come up the bottom and suspend them in the tube a little longer with the gas coming up from the bottom.
All right.
And so it's all these little subtleties with respect to how you manage that process that really give us great control, but also, of course, adds a little bit of complexity to just a heated steel tube, if you like.
Yeah, yeah. So when you have the powder at the end with the enormous surface area on every particle, what's the next step?
So with our water treatment business, for example, that very high surface area powder, we basically mix with water. And because it's such a high surface area, it reacts to form what's called a magnesium hydroxide slurry. Sorry for the chemistry there, but basically it's a looks like a paint. It's like little particles in a water or liquid paint, and that's what we dose into sewer systems and wastewater treatment plants. And so that very high surface area enables us to make that reaction to form the final product very simple. It just reacts straight away with water. And so that's one example, for example.
Is fertilizers another?
And fertilizers is another. In fact, we start with a very similar material. It's a magnesium-based material, and we mix it with water at the end, and ultimately spray that on a crop on a farm. Yeah. And so, and again, the high surface area gives us specific properties that enables us to do that quickly, and also that enhances some of the crop protection aspects of that particular product as well. So there's numerous sort of, I guess, end markets for that particular product based upon magnesium. But we also can process limestone, as I said before. We can process manganese, which is a battery material that we're experimenting with. It's a very versatile calciner that we can put all sorts of different materials through.
And in the building industry, which of course we had in episode 1, which is where the business started, the main advantage of what you produce, tell me if I'm wrong, isn't the higher reactivity. It's the fact that you can capture and remove the carbon. So it's environmentally friendlier, but I guess with the same properties.
Yeah.
Is that right?
Exactly right. So in the building industry, we'd started to try and make magnesium-based building products. So the cement industry at the moment is all based on limestone. And what we started to look at was basing on magnesium. Magnesium is slightly lower temperature, so it's a little more environmentally friendly. And of course, again, we try and capture the CO2 out of that process. So that was the basis of the original building products idea.
Yeah, right. And you're doing some work in Belgium with that?
Yeah, so in Belgium, we're looking at the limestone, the traditional cement-based building product, and that's really for the CO2 capture piece. So as you may recall, half the weight of a lump of limestone is CO2.
Yes.
Our process can separate that directly. That's actually 2/3 of the emissions of the cement and lime industry is coming out of the rock itself. Wow. And so our technology is being trialled with Heidelberg Cement and Cemex and these quite large cement companies, because suddenly they're interested in mitigating their CO2 emissions. Well, they're becoming much more interested over the course of the last couple of years. And so that's the project that we're developing in Belgium.
So what do you think the big, apart from the ones you've mentioned, so you've mentioned fertilizer, wastewater and cement, what are some of the other big challenges and opportunities at the moment that you see?
Yeah, it's interesting because, again, if I go hark back to what really attracted me to the company, very high surface area particles are very interesting to look at in a whole lot of different applications. And I don't want to scare people off with all the skunk works that's going on in the company, but we're looking at a marine coating that helps stop fouling. And again, that's just a high surface area.
Fouling?
Yeah, like, barnacles forming on boats and these sorts of things.
And what do you mean by skunk work?
Oh, skunk works are just, the Friday afternoon specials, where we just have a look at all the different ideas.
Throw some ideas
around and that sort of stuff.
Well, throw them out here.
Throw them out here. Okay, righto. Well, there's so marine coatings, high surface area magnesium oxide particles, just in a marine coating to help stop barnacles forming. Barnacles are they're rather unpleasant if you rub up against them, of course. But of course, a ship doesn't like them because it increases the drag.
Yeah.
And then you're using 10, 20% more fuel. So they're a big deal. So helping stop barnacles grow is one of the things we're working on. We're working on other extractive mineral processing technologies, like to get a lithium ion to put in your phone or your car, you have to crush up a rock called spodumene.
Spodumene?
Spodumene.
What a great name.
I know. And then you heat that up. And then the gas is driven off and the crater pour, and you get acid in there to soak the lithium out. And, of course, what our technology can do there is do that more efficiently. Remember, we can make more pores. We can get the acid going in to be a bit gentler, extract more lithium. So in mineral extraction technology, the technology is also applicable there. So that there's all sorts of different avenues for us that we're pursuing.
One more?
One more.
I like this bit.
Yeah. One of the other things that we're looking at, and it's similar to the crop protection and marine coatings piece, is pharmaceuticals. And so again, initially we're looking at the potential for the product in topical ointments, like to help stop bacteria and these sorts of things spreading on a burn or a wound.
Increase reactivity, do its job quicker. Is that kind of it?
That's kind of it. Yeah. We know the bacteria don't like our particles. It doesn't kill them. They just don't like them because that very high surface area is something that they don't like. It's these what's called reactive oxygen species, by the way. I don't want to get too technical, but the edges of the crystals in those pores, the bugs don't like them and they go off elsewhere. Yeah, right. And so it's a way to help prevent bacterial infections. And so that's another area that we're exploring with the same technology.
Where would you like to be with this technology in 20 years? So just before you answer that, no one's going to remember what you said now in 20 years. So, you're not really that accountable. You might as well just dream big and say something ambitious, eh?
Oh, look, I think everyone in the company is incredibly ambitious because we can see how the one core technology can lay across a whole lot of challenges that the globe currently faces. So in 20 years' time, we're the best technology and the most utilised technology for CO2 mitigation in lime and cement. Yep. So we're in every lime and cement plant in the world, stopping that CO2 getting into the atmosphere. In water treatment, we've replaced a lot of caustic that's currently used in water treatment. Caustic soda is very nasty. It adds sodium into inland freshwater rivers. Our product is magnesium-based and it's much safer and more environmentally friendly. So we've replaced a lot of the caustic used in those areas there. I haven't even sort of talked about batteries too much yet.
Tell us a bit about batteries.
Yeah. With respect to batteries, I want to see our technology starting to form the basis of, certainly 20 years will be the basis of a modern lithium-ion battery. And again, we're just starting with a different mineral called manganese. And manganese was actually one of the original cathodes in a lithium-ion battery. But it didn't really last as long as modern lithium-ion batteries. But they add a lot of nickel and cobalt and this sort of stuff, which are very expensive and poisonous and hard to recycle. We're trying to reshape back to manganese oxide with our special porous structure, if you recall. Lithium ions can move in and out of it easily. It's quite flexible so it doesn't break down, and so your charging of your phone doesn't deteriorate over time. So in 20 years' time, I want our chemistry to be back at the forefront of lithium-ion battery technology, and obviously that's a big ambition, but it's a huge potential market, obviously, as well as electrification of cars and these sorts of things take place. So there's a lot. There's a lot we want to achieve. There's a lot in the skunk works, James, that may come through as well.
A lot of the skunk works, yeah. And also, no doubt, things you haven't even thought of yet.
Exactly
that you
right.
will.
Yeah, exactly right. I think we've got a great young talent coming through the organisation, and that pipeline of talent will no doubt find a hell of a lot more than we've been able to think of just at the moment as well.
What about risks? Are there things you have to be wary of?
Of course. There's always risk. The company's founded on technology and intellectual property. We need to be not only protective of our intellectual property, but always ahead of the game. We need to continually improve so that anyone who did try and copy, obviously, we'd want to stay well ahead of them.
Yeah.
So key risk there is really about continuing to have an innovative mindset and continue to advance the technology forward. The other risks, I guess, we face are typical sort of commercialisation risks. You may have a great product and a great idea, but as with building products, for example, we headed a long way down a pathway and found it was the right solution for the wrong market, if you like. And so we need to be very conscious of prioritisation and not putting a whole lot of resources into something and fail fast, if you like. Yeah. With so many options open to us, we don't want to, get distracted, if you like, with things that aren't going to actually pan out for us well. And so balancing resources with focus is one of the key risks that we constantly have to manage. But, yeah, it's a happy problem, ultimately.
You mentioned retaining an innovative mindset.
Yep.
And it can be many companies that start off innovative get to a place of comfort and without ever meaning to, they, just focus on servicing their clients and giving their clients what they gave them yesterday, and all of a sudden they're not being that innovative anymore. They're just doing today what they did yesterday. How do you as you prosper, how do you guard against that complacency?
Yeah, it's a constant challenge, as you know. Most companies would, as they get bigger, put in the processes to help manage that size, and ultimately that tends to cycle back and stifle innovation a bit. I think we've got a very sort of laser focus on keeping the company small enough. Yep. And we all know each other. We're all a team. We all have an innovative mindset. And as businesses mature and reach the top of their sort of innovation cycle, if you like, those businesses are great to spin out or go off and do their own thing. I think the core team is really about keeping that smaller innovation mindset happening while the technology is still there to continue to spin out those ideas. And so, while I'm here, that's certainly the way that we'll be approaching it.
Yeah. Although challenging, isn't it? Because you would have had a tough nearly 10 years since you joined the company. You went through some difficult times and now you've clawed. I mean, at times you just must want to chill out a bit. How do you know what I mean?
Yeah, no, look, I think, certainly what drives me, and I guess what drives a lot of people who work for me, who work horrendous hours and do all those sorts of things for the company, are the fact that a lot of these things that we're doing can address some pretty serious global challenges right now. And so it's very motivating to work for a company and to work for a technology that has that potential. The last 10 years has absolutely flown past. So I'm not feeling tired or jaded or anything right now. I could just looking forward at the potential.
Fantastic. Is there anything else you want to add before we end?
Watch this space. Watch this space. Watch what the skunkworks spin out over the next few years, James. I'm sure it'll be quite an interesting new dimensions to the company as the next few years pass.
Yeah, good to talk to you. That was very interesting. Thanks very much, Phil. And next time on Innovating for the Earth, how the Calix technology can contribute in a bit more detail to direct climate action.